Hello, I am Dr. Zenya Worth, and in this video, we will be discussing numerical integration. We will go through the different types of numerical integration techniques, and we will finish with a couple of example problems and a practice problem. Numerical integration is an approximation. You approximate an integral using numerical techniques. Instead of evaluating the integral directly, maybe you can't, maybe you don't know the solution, maybe the solution is very difficult to find. Whatever the reason, you cannot evaluate the integral directly, so we sum the area under the curve by creating a series of shapes and then evaluating the area of those easy-to-find shapes. Common shapes include rectangles and trapezoids because it's very easy to find the area of those shapes. The thinner the rectangles or trapezoids, the more rectangles and trapezoids that you use, the more accurate the approximation is going to be. In general, we approximate the integral by dividing the area into equal subintervals, and that each subinterval has a specific length delta x, and then we compute the area of each rectangle or trapezoid that has that length delta x, and then sum the areas to find the area under the curve. When we approximate using rectangles, there are three different ways that we typically go about doing so. The first is the left-hand rule, the second is the right-hand rule, and the third is the midpoint rule. For the left-hand rule, the left corner of the rectangle touches the curve. In this example, we have a curve shown in purple here that is underneath my rectangles, and we're approximating the area of that curve using a series of rectangles. But you see that the corner on the left of each rectangle is actually touching the curve. This method tends to over-approximate the area because we have extra area of rectangles that are above the curve and shouldn't be the area under the curve. We also can use the right-hand rule, and in this case, the right corner of each triangle is going to touch the curve here. And this tends to under-approximate the area because you have empty space underneath the curve where the rectangles aren't actually part of the curve. To solve some of these issues with either over-approximating or under-approximating the area, we can also use the midpoint rule, where the midpoint rule, I have the midpoint of each rectangle is actually the point on the curve. So we overestimate a tiny bit, underestimate a tiny bit, but it tends to be the most accurate of the three rectangular methods. Each of these rules has a mathematical definition. So I just showed you what these rules look like graphically, but you can also do it mathematically using summing. But the first thing you need to do is determine the length of each subinterval, which is delta x. And this is going to be based on the limits of integration and the number of subintervals you want. So that's n, and you choose n. The more subintervals, the more accurate the approximation. We define the length of each subinterval or the length of each rectangle, the base or the width of each rectangle, as delta x, and that is b minus a over n. Mathematically, you evaluate the sum of each of these rectangles using one of these formulas for the left-hand rule, the right-hand rule, and the midpoint rule. To make it easier to start the problems, choose your n value or the number of rectangles or subintervals you want, and write out the actual intervals you have. So write out the actual x values that you're going to use in those intervals. Then you're going to use the formulas below. For the left-hand, right-hand, or midpoint rule, it is the sum from I equals 1 to n of the function of x and whatever placeholder of x that you have times the length of the subinterval delta x. So writing out the actual intervals themselves will be very friendly because it will give you the x values that you need to evaluate the function. So you're evaluating that function at that point x, and you know what those x values are going to be. For the midpoint rule, it's a little more complicated, but we'll do an example and you'll see that you're taking whatever x value is in position n minus 1, you're adding it to the value of x and n divided by 2. And then we include also the trapezoidal rule here, where the trapezoidal rule, instead of creating a series of rectangular areas and summing those, now you're creating a series of trapezoidal areas. The trapezoidal areas, there's a slight change in the height. So that's why these are very long, thin trapezoids instead of rectangles. And actually, you're approximating the slope of this curve at every point with a linear approximation. And these shapes end up becoming a trapezoid. So this tends to be more accurate than the rectangular approximations because you can change the slope of each of these trapezoids to more closely align with the curve at every subinterval. And the trapezoidal rule is here. You take delta x out in this case, and you have a slightly more complex method of summing that includes a constant 2 and includes x naught and xn. And we'll go through an example where we use this and you can see it being applied. So let's practice with a problem. We'll do all of these integration methods using this problem. So in this case, we have the integral from 0 to 4 of negative x squared plus 16. This is a fairly friendly integral to actually integrate, but let's say that for some reason we don't know how to integrate this and we need to actually approximate it using these numerical methods. Let's start by determining the length of our subintegral. If the limits of integration are 0 and 4 from the integral, then we need to choose some subintervals to divide. To make it easy and to make the math more friendly, we're going to have 4 subintervals, so n is going to equal to 4. So we're going to have 4 rectangles or 4 trapezoids. I wrote out my intervals here. If we have 4 subintervals, there's one from 0 to 1, there's one from 1 to 2, there's one from 2 to 3, and there's one from 3 to 4. So we have actually 5 x values here. We have x0, or x naught, x in the first position is actually x0. Then we have x1, x2, x3, and x4. So we have 4 different positions for x values. And that's going to be important when we actually evaluate the numerical integrals. And our delta x value, which is why I chose n equals 4, is 4 minus 0 over 4, which is n equals 1. So the length of each subinterval is 1. Let's either choose the left side, the right side, or the midpoint of these rectangles to evaluate the function in sum. So we'll do those first. If we're using the left-hand rule, we're using the left side of each interval or the left corner of each rectangle to evaluate, which would give us the x points 0, 1, 2, and 3 in our interval set. We plug those points into the original equation f of x and solve f of x at those x values. So that is what's being described by this sum here, sum of I equals 1 to n. If we plug in I equals 1 to here, we get x naught, or the 0th position, or the first position of x in our interval. And the first position of x in our interval is x is equal to 0. We evaluate the function at x is equal to 0. So we plug 0 in for x here and see what f of x is equal to. And we multiply that by delta x, where delta x is the length of our subinterval. In this case, it's 1. So that's step 1. But we still have some I values to go. If I is now equal to 2, well, 2 minus 1 is equal to 1. So we need the x value in position 1. The x value in position 1, or the first position, second position, I guess, is 1. X is equal to 1. So we evaluate the function at x is equal to 1, negative 1 squared plus 16, and I multiply that by delta x. Now I do for the third value of I, which is 3. 3 minus 1 is 2. So I need the second position of x, and the second position of x, the x value is also equal to 2, because the math is friendly that way. So that is x is equal to 2. I evaluate the function when I plug in 2 here, and I multiply that by the length of my subinterval. And then my last is I is equal to 4, because I is equal to n in this case. 4 minus 1 is 3. What is the third position of x? The third position of x is this one. We have x0, x1, x2, and the third position of x is 3. So I evaluate whatever the third position of x is. In this case, that's equal to 3. Plug in 3 here. I find whatever f of x is equal to, and I multiply that by the length of my subinterval. And this is how you would do this numerical approximation. It's a sum of this formula. So if I plug in the values here, f of 0 is actually 16. I plug in 0, that goes away. F of x is equal to 1 is 15, et cetera, et cetera. And I find that the actual approximation of the area is 15 plus 16 plus 12 plus 5 is 48. Let's do the same thing, but now we're going to use the right-hand rule. For the right-hand rule, the right corner is where I'm evaluating these points at, or the right side of the rectangle. So I'm using the right-hand corners of these rectangles, which are actual, the points on the x-axis are 1, 2, 3, and 4. So this is x at position 1, x at position 2, x at position 3, and x at position 4. And again, we plug those points, those x values in for our original equation f of x and solve. So in this case, I is equal to 1 from 1 to 4. So at I is equal to 1, we have the evaluating the function at the first position of x. The first position of x is the x value of 1. So I plug in 1 here to the equation, and I find whatever f of x is where x is equal to 1. Times the length of my subinterval delta x. Then I do that for the second position of x. So if I is equal to 2, that's the function of second position of x, x2. And in this case, the second position of x is actually the value 2 for x. So x is equal to 2. The function evaluated at x is equal to 2 is negative 2 squared plus 16. I do the same thing for the third position of x, where the x value is equal to 3. And lastly, the fourth position of x, where x in the fourth position is actually x is equal to 4. So I plug in 4 here to my f of x and solve for f of x. And again, every time that I do this summation, I have to multiply by the length of my subinterval delta x, which is why each of these is multiplied by 1. I do that sum here, and I find, based on the right-hand rule, that the area under my curve is 32. This is significantly less than 48, and we are under approximating the area here. Let's try to do this for using the midpoint rule. For the midpoint rule, we use the midpoint of each interval to evaluate. So in this case, if you look at the formula here, we find the position xi minus 1 plus xi. If x is equal to 1, or if I is equal to 1 here, we would plug in I minus 1, or 1 minus 1 is 0, so that's the x naught position, plus x is equal to 1, that's the x1 position. So we would have whatever the value of x is at the 0th position, which would be 0, and whatever the value of x is at the x1 position, which would be 1, that would be 0 plus 1 over 2. And 0 plus 1 over 2 is 1 divided by 2, which means the x value is actually 1/2. So I plug in 1/2 here. So I take this 0.5 or 1/2, and I plug that into my equation for x, and I find f of x. This is what I'm doing for the midpoint rule. I'm taking the midpoint of each subinterval. The midpoint of the subinterval from 0 to 1 is 0.5. The midpoint of the subinterval from 1 to 2 is 1.5. The midpoint of the subinterval from 2 to 3 is 2.5. And the midpoint from the subinterval 3 to 4 is 3.5. So those are my x values here. And I plug each of those x values back into the function, and I solve for them. Always remembering to multiply whatever the value of the function is at that point. I always multiply that by delta x, which in this case is 1. So I do that sum once I've evaluated the function at each of these points and multiplied it by the length of the subinterval. And I find that the area under the curve is approximated as 43 if we use the midpoint rule, which is higher than 32, but lower than 48. And we're getting a more accurate approximation here. Finally, we can use the trapezoidal rule. We will have the same interval, 0 to 1, 1 to 2, 2 to 3, and 3 to 4, but we approach it a tiny bit differently. We plug each of the x values from our intervals into the function f of x and solve according to this trapezoidal rule formula. The first thing we do is we leave delta x over 2 to the side. So we're gonna just leave that off to the side and deal with that later. And then we come in here and let's take a look at this. So first, the first thing you evaluate is f of x where x is in the x naught position, or the initial 0th position of x. The 0th position of x in this case is 0. All of these intervals. The first position of x that we're integrating is the 0th position, which is 0. Then we take the sum of multiplying the f of x from I equals 1 to n minus 1. But every time we do that, we multiply it by 2. So every time we take or evaluate the function of x of I, as long as it's not the 0th position, or as long as it's not the last position, this is I equals 1 to n minus 1, we're going to multiply whatever that is by 2. So that actually gives us a trapezoid. And it's hard to see it in this form, but I encourage you to write this out or try to write out the area of a trapezoid, and you will see that it will actually simplify into this form. So for the x1 position, where x is equal to 1, we multiply that by 2. Evaluate the function at x is equal to 1 and multiply it by 2. For the x I equals 2 position, so x2, that value is actually 2. We multiply that by 2. When we evaluate the function at the third position of x, where x is equal to 3 in this case, we multiply that by 2. But then for f of x is equal to n, which in this case is the fourth position, x is going to be equal to 4, and we evaluate that without multiplying it by 2. So we don't have a constant here, and we don't have a constant at the 0th position. And then we multiply that whole expression by delta x over 2. And in this case, delta x is 1, so that'd be multiplying it by 1/2. So this is what it looks like. We evaluated the function at each of these points. X is equal to 0, 1, 2, 3, and 4. We sum that up here. We multiply them by the constants if we needed to. And we find that according to the trapezoidal rule, the area under the curve is 40. Now let's check these approximations against the actual value of the integration. So I'm going to integrate this, remembering my rules for integrating polynomials, and I find that the integral is -1/3 x cubed plus 16x, evaluated from 0 to 4. So if I plug in 4 for every x value, and then I subtract 0, because if I plug in 0 for both x values, both expressions are 0. And I find that the actual area under the curve here is about 42.67 or 42 2/3. In this case, the midpoint rule was the most accurate approximation because the midpoint rule gave me a value of 43. Often you'll see that the trapezoidal rule will be slightly more accurate than the midpoint rule, especially if your curve function is a little more, has a more of an interesting shape. You can get a more accurate approximation with the trapezoidal rule. And in general, if we had increased n, or if we had increased the number of subintervals, we would have more accurate approximation. There is one more numerical integration method that I would like to discuss, and that is called Simpson's rule. Instead of approximating with rectangles, which have a flat horizontal slope at the curve, or approximating with trapezoids, which have a linear shape at where the curve is, we can approximate our function with many functions that have a wide variety of slopes. We could have a constant slope like a rectangle. We could have a linear slope like a trapezoid. We could have a parabolic or a quadratic slope. We could do whatever slope that we want for the very top of my shape that most closely approximates the actual shape of the function at that instance in that subinterval. So we can vary it, we can change it, we can add a bunch of different areas. It makes them harder to analyze, but doing that in a numerical method is what we actually call Simpson's rule, is where we can give it a little more variability in how we approximate the shape. However, to use Simpson's rule, the n value, or the number of subintervals, has to be even. This is the mathematical description of Simpson's rule. So we boil down all of that variability in how we approximate the shape of the curve, and we boil it down to this formula. Delta x comes out, and delta x over 3 is what is multiplied by everything in here. And in here, we have sort of an alternating constant. The initial position of x, x naught, and the final position of x, x to the n, are not going to be multiplied by any constant. But every odd numbered I value, I is equal to 1, I is equal to 3, I is equal to 5, whatever odd numbered I value, you're going to multiply f of xi times 4. And every even numbered I value, so if I is equal to 2, I is equal to 4, I is equal to 6, etc., you're going to multiply the expression of that function by 2. So odd numbered I values, you apply a constant of 4 to that. Even number I values, you apply a constant of 2, and you alternate until you get to the second to the last n value, which is going to be an odd numbered n value because n has to be even to apply Simpson's rule. You're going to multiply that by 4, and the very last n value, or I value, which is n, you're not going to multiply by any constant. So for our previous example, our x naught value, the value of x at position 0 was actually the value 0, x is equal to 0. The value of x at position 1 is x is equal to 1. You calculate the function at x is equal to 1, and you multiply that by 4. For x2, x in position 2, the value of x was actually 2. You evaluate the function at x is equal to 2 and multiply that by 2. Since x3 is an odd numbered I value, you multiply that by 4. And lastly, the last value of x is at position 4, where n is equal to 4. And then you evaluate the function at x is equal to 4, and you don't apply a constant there. You multiply that entire evaluation by delta x over 3, and delta x is equal to 1. So this is what the expression will simplify to when you plug in the x values that you need into your function, and you find that using the Simpson's rule, the area under the curve is 40. As curves get more complex, as they have higher order polynomials, as your integrals get more complex, you find that Simpson's rule is also very accurate and tends to be more accurate than just a rectangular rule. I encourage you to practice what we reviewed today using the following integral here. Again, from 0 to 4, I encourage you to choose n is equal to 4, or maybe n is equal to 8, so you have the intervals. And I encourage you to practice approximating this integral using all 5 techniques that we discussed, and then compare that to the solution of the definite integral and actually integrate this and compare. I hope you will find this video useful in your class.